Hey, good afternoon, everybody. My name is Cowdery-Corvan. I'm currently a fifth-year software engineering student at the Rochester Institute of Technology, and I'm also from around here. I graduated from Harley in 2007, and I'm also a lifer. And I had a fantastic time there as a student, and hey, they still can't get rid of me. And I work at Apple on iOS. And I got there in part because of this guy, and I've always wanted to get into computers, but I didn't realize that I really wanted to get into software development until I took APCS with Mr. Wilcox. And as much as I'd like to talk about my life, I'm here to talk today to talk about how awesome software engineering is. And please note that I'm very biased on the matter. At the end of the day, I'm just a dude, so take my advice with a grain of salt. But yes, coming back to the original question, what is software engineering? So we got four pictures of things here. We have World of Warcraft, we have Call of Duty 4, we have an airplane, and we have the New York Stock Exchange. So what do they all have in common? So hopefully it won't be too much of a reach to think that all of them have a code in common, and a lot of it. So just for a little bit of a frame of reference, a Boeing 747 has more lines of code than it does parts, including nuts and bolts. So I was really blown away by when I heard this. So how much lines of code? So specifically, a Boeing 747 has 4 million lines of code in it. And most games that you play today have about 6 million lines of code in them, just for reference. So these are really huge software systems that really can't be thought of at like one line or one class at a time. The software engineer needs to think about the design at different levels, from one line of code all the way up to the entire system. So let's think about scheduling that for just a moment. So if I can write one source line of code per minute, there's 60 minutes in an hour, and there's 40 hours in an average work week. That gives me 2,400 source lines of code per week per software engineer. So if we take that, and we multiply that by the usual 50 work weeks per year, that means every software engineer can crank out 120,000 source lines of code per year. So pulling that all together, if I have 2 million lines of code estimated in a project, with the amount of code I can crank out from each engineer, I need at the very least 17 software engineers to get this on the software shelves for the holiday season. So you get a feeling that these things need to be planned out a lot, and also that you have to work in teams. And also, writing one line of code per minute on average, believe it or not, is actually pretty hot shot in the software industry. And actually, it really is. Mainly because so much of your job as a software engineer is so much more than coding, and you'll see that pretty soon. So let's talk about one company you may have heard about, Amazon.com. And it's one website. It's relatively large and pretty complex. And the software team was going to go do one small software upgrade. Pretty easy. But the upgrade didn't go out so hot, and it caused a 90-minute outage. So, is that priceless? Not exactly. Estimated cost to Amazon was $2.8 million in lost revenue. Now, that's not just revenue that they lost from customers where they could have come back later and bought this product later. No, this was actually $2.8 million that Amazon lost because the website was down, the customer needed something then, and they lost that $2.8 million. So somebody got fired. So the system wasn't safety critical, but it is financial critical. So this team needed a better understanding of the process for developing a critical system and how to bring an upgrade online without taking down the system. In this case, Amazon would have benefited from a better defined software development process. So, as a software engineer, you have to answer a lot of questions. So, one question is, how much code do I have to write? And you're pretty already familiar with that after taking AP Computer Science. But there are a lot of other questions that remain too. So, how can I help the customer? What's required to solve the customer's problem? How will the user interact with the system? What operating system, language, hardware is going to be used? What is the overall software system structure, and how do different components interact with each other? How do I organize my team so we're all effective? And can we finish the game in time to have it on shelves for holiday shopping? So, the real common trend here is that you have to talk to a lot of people to make this happen. So, you have to interact with customers who are asking for the system, people who will use the system, domain experts, banking, avionics, security, medical, scientists, engineers from other engineering disciplines, and even most closely with other engineers on the project. So another big underlying theme here is communication. Software engineering is a very social activity. You don't sit in a cube and write code in a corner. You're always working with people, and it's a very people-driven field. But that doesn't mean that software engineers don't get their hands dirty writing programs using the latest technologies and techniques. We live and breathe that as well. And also, it's important to note that it's not just project management and communication, but it's also not about coding either. So, by now, you might be seeing that software engineering doesn't exactly equal CS. Both majors try to solve real-world problems using code, but how they go about that is very different. So for example, if a bridge falls down, is it the scientist or engineer's fault? Well, not so much the scientist, more the engineer. So scientists build things to learn something new, and engineers learn things to design and build quality products. So scientists want to achieve scientific breakthroughs. Engineers want to avoid engineering failures. Computer scientists want to understand the algorithms and the foundations of computing theory, whereas software engineers want to learn and design the principles of best practices for building quality software systems. And lastly, computer scientists want to know the basic technology works and how to improve it, whereas software engineers want to know the characteristics of technologies so they can design the most appropriate technology into their software systems. So you get the idea. So let me illustrate this with an example. So in addition to working at Apple, I also work here for Wegmans as my senior project. Part of my graduation requirements as a software engineering student is I have to work for a company for about half a year, a little bit more than that, effectively 2 trimesters. And I work on software for cheese. And here's the problem we're trying to solve. So as it currently stands, Wegmans is responsible for really getting into the cheese market, and each individual store has to track all the cheese that it has in each store, and it has to go and order these cheeses from independent vendors all throughout the world. So that means that it has to have contracts with vendors in France and UK and Wisconsin, and has to manage all those independently. So if this was just one retail store, that would be fine. But Wegmans has 81 retail stores across the United States, each with their own contracts. So this gets to be a pretty big problem pretty quickly. So moreover, another problem that can exist is if the store receives too much cheese, that's actually pretty bad, because if the store isn't able to move the cheese in time, the cheese goes bad, and then you have lost profits due to lost sales in cheese. On the other side of the coin, if cheese is desired, but the supplier can't provide it, that's also bad, because then at that point in time, you get angry customers. And Wegmans is really striving to have a consistent quality customer experience, and that neither of those would be beneficial to that for Wegmans. So the solution for Wegmans is to build a central facility for processing all of their cheese. So this central affinage facility has contracts with all the vendors all around the world. They receive the cheese, age it, and then negotiate with stores individually, and then ships the cheese to the stores, so that they have the correct amount of inventory exactly when they need it. So the software system that we designed has to process the cheese all the way from a vendor delivery all the way to when it ships it to the store. So that means quality control, rejecting the delivery, accepting delivery, and everything from an order management perspective. We learned a lot during there. And in 1 year, a team of 5 students, e.g. my team, made 26,163 lines of code. And some of it was generated by scripts, but you can see that there's a lot of code that goes into making the system work. And we really can't think of it on a lines of code basis anymore. We really need to think about this system in terms of boxes and lines. What are all the systems that are interacting with each other, like a very, very well-oiled machine? And there's a lot of things that sit on top of each other, things that interact with each other, and as a software engineer, it's really my responsibility to make sure that all these things are playing well so we can release a quality product to Wegmans. But on the other side of the coin, I also speak computer science. I have some experience with computer graphics and computer vision as my forte. And Right now, I'm currently working on an iPad application that actually has real-life painting. It's going to go on the App Store next week, so that's kind of cool. When you can tilt the iPad, it gets the angle of the iPad. It actually simulates brush strokes and pushing paint around, so it's kind of unlike Photoshop, where if you like draw over a certain area in Photoshop with one color and you draw over it again, it completely overwrites what you had. But now this actually blends the paints together like you would on an actual easel. So it's really cool stuff. And that's some research that I'm doing with the computer science department with computer graphics. So that's one possibility, but what I really want to talk to you about is some of the research I've been doing with pedestrian tracking. So pedestrians, they can be articulated in many different positions. You can see them biking, you can see them hiking, you can see them walking, you can see them skiing. There's many different ways that you can see them. So the challenge becomes that you have to write a function, f of x equals pedestrian, at the end of the day. And being able to do that for all these different types of people is really mind-boggling. So do you do it based off of color segmentation? Do you do it based off of how they're standing? There's so many different ways you can attack this problem and so many different trade-offs that you have to make, both performantly and accuracy-wise, to make the best product possible. So I'm going to talk to you a little bit about some of the research I did for this. And pedestrian detection really falls into two schools of thought, much like all object detection in computer vision. And that is, you can either have a parts-based detection or holistic detection. So parts-based detection tries to identify the individual parts that make up a master object and tries to see their spatial relationships with each other, and then determines whether or not that object is really the object that it believes it to be. And we're going to illustrate that in just a moment. On the other side of the coin, there's also holistic detection, which takes a look at the entire image in multiple sections and tries to determine for that specific window if the object of interest is actually there. So, for example, in the parts-based, we can first detect the legs, we can detect the face of a person, we can then detect the arms, and we can detect the torso. And then if we draw like basically a stick figure of all these different relationships with all these parts, that is an acceptable geometry for the lengths. So we're going to say that because we detected a face and a foot there, that this is going to be a pedestrian. That's great, and we're going to lock that on right there. On the other side of the coin, there's a holistic detection, which again takes a look at individual sections of the image, keeps drilling it down into a very fine-grained pieces until it can finally find a pedestrian in those areas, and then says, bam, an object is there. Where some of my research came into play is that I combined both a parts-based approach and a holistic approach, where we basically just look at individual body parts and use that as a scoring mechanism for where pedestrians actually are. So in other words, I get a rough idea, is there a foot here? And if there's a foot here, chances are there's a person up above you. If you have a face here, that's great. Chances are you have a person behind you. And this is really useful because the connect the dots example where we detected whether hands and faces were close enough to each other to be a person is actually really computationally intensive, because there's so many different ways a person can be standing or sitting or kneeling that becomes really hard. So being able to kind of suggest where a person might be and then take a look at that specific frame is really computationally efficient, because when we can limit the space of where these detectors have to look, it saves us a lot of time. Because just take a look here. The code that you're seeing, or rather the detector array that you're seeing here, is the code that trains what our computer vision systems are using for detecting where pedestrians are. And as you can see, that's massive. Being able to run through that on a 30 frames per second basis takes a lot of computational power, and it was really important to kind of cut that down. So just kind of a little bit of an example is, given this image, what we first do is we then kind of look for different parts. So for this example, we found a face, we found a lot of different other body parts on the person on the right, we found the hands, we found the torso. We also found some other bad things as well. Like, you can see that it kind of found something in the middle of nowhere, it found a power transformer, it found a door, thinking it's a torso. There's a lot of things here that weren't exactly perfect. And we say, hey, there's probably a person in this area over here. And when we do that, we limit the area that we actually have to look at. And when we can run detectors in that specific area, that means we're running a whole lot less of that really, really huge code that I showed you, just so that, we can have much more performant results when we're trying to detect pedestrians. So basically what happens is this works with a very heavy statistical model trying to determine if there's a pedestrian here, there's a much higher chance that there's going to be another pedestrian in this area. And we have other different classifiers that run through and say, hey, there's a pedestrian around here, and this is where you can find them. And we have these different techniques called voting spaces and Haar wavelets that we use to detect where these pedestrians are. And then lastly, we put that out to a display output system to determine or to show where the pedestrians actually are. And a few moments later, it was able to turn it into a paper, and that was really cool stuff because being published as an undergraduate was pretty fun stuff, and it was pretty nice. And there's really just so much that you can do in computer science. Computer graphics and computer vision are really just kind of scratching the surface there a little bit. And one field that I'm just starting to get into is natural language processing for a personal project of mine. And guess who knows a thing or two about the subject? I'll give you a hint that look in the bottom right-hand corner and, might surprise yourself. But, it's kind of cool when you see those things pop up. But now that you kind of have a 30,000-foot view for what computer science and software engineering is and what some of the differences are between the two, hopefully now you'll be a little bit better armed. If you are kind of going into a computing major, you now have a little bit better, hopefully, understanding of what the differences are between software engineering and computer science. So again, kind of a little bit to recap. So software engineers are kind of responsible for making reliable, commercial, and sometimes open source software systems on any platform of any size for a customer typically, and also in a team. And computer scientists, on the other hand, dive into the underpinnings of computing and knowledge and really try to fundamentally push the frontiers of what computers are capable of doing. And it can kind of be crudely thought of a question of, do you like applying code in practice, or do you really like researching the theory behind it? And really what the best part is that we really just scratched the top of the iceberg here. So there's so many opportunities available in computing. There's geospatial information systems that make sense of the world around us, financial systems, human-computer interaction, usability, virtual reality, telecommunications, education, health systems, you name it. What's really awesome about being involved in computing is there's really a demand wherever you go. So the job market situation is looking really excellent for both myself and my classmates and really anyone that's in our major. So hopefully that can get you started on thinking about what you want to do next. The world is your oyster. But if you are thinking about being a software engineering or computer science student, I just want to give you a few tips and basically kind of hash out what a day in the life is for me as a freshman in software engineering at RIT. So first off, it's awesome. It was really awesome. So again, I'm very biased on the matter, but I think it was really a fantastic experience. And there's a lot of social opportunities, for example, that's me going on a camping trip with some freshman friends I made in the first 2 weeks. So there's a lot of social, fun things that you can do. And also there's a lot of work in studying too, but it's kind of a work hard, play hard sort of thing. So at Harley there's a lot going on, but it's happening in a small enough space that it's not hard to kind of get a feel for what everyone's doing just by asking a teacher, a friend, or getting kind of the lowdown from morning meetings. That's really not the case at college. You really got to take the initiative, get out and meet people, and really just try new things, because things aren't really going to come to you. And that was hard. Harley does such an awesome job, again, of keeping you in the loop and having a tight community. And when I left that, it took a little getting used to being proactive and trying to find clubs, making new friends, and all that was really weird. But, rest assured, you're coming from Harley, you're an elite strike force of seniors or perhaps juniors, and, you're going to be awesome at it. So just give it some time and patience. But yeah, I guess the one thing that did catch me off guard, though, about being in college is being a lifer. I'm really used to having small classes with not a whole lot of people. Like, for example, my function, statistics, and trade class that I took with JAM, I had 3 students in that class. But when I got to RIT, I was surrounded by people, and that took a little bit of getting used to for me. But it wasn't bad, just caught me off guard at first. But, even though there are a lot of people at RIT, your professors still care about you, and they can still be your friends, just like at Harley. So really don't be afraid to approach them. They're human beings at the end of the day, and they really care. I'm on a first name basis with a lot of my professors, and I occasionally go out and have beers with them and stuff like that, so it's really cool. So again, I guess a little piece of advice is get to know your professors, and you'll be really glad you did. And not only the professors are they really cool people, but they also know a lot. So a couple days ago, I had a chat with my information systems professor and left with 8 books, some borrowed and some he gave me, and just everything. Just like went up to his office and said, "Hey, can you teach me a little bit about web design and some of the questions I had?" And I walked out with all these books. It was crazy. So on the topic of books and work and stuff like that, as a freshman, I averaged about 20 hours of homework per week. A general rule of thumb is to multiply the number of classes you're taking by 4. And that's roughly how many hours of homework you're going to be chewing on per week, including weekends and stuff. So here are the courses that I took as my first quarter at RIT. Your first schedule is usually made for you, and after that you're on your own to pick what you want, similar to Harley, with the assistance of your academic advisor. I'm putting calculus in a star because if it's at all possible to take calculus at Harley, I strongly suggest you do so. You have very qualified people who care about you, and calculus for me at RIT, when I was just transitioning to a new school as well as something in math, which has never really been my forte, that was really crazy for me. So if you can take it at Harley, so much the better. But I digress. Here's kind of the general overview of courses you would take as a software engineering student. So first year, you focus a lot on the computer science, fundamentals, calculus, the sciences, some of the liberal arts, and also discrete mathematics. It's not really a whole lot of what you touch on at Harley, but it's really talking about like logic, sets, and things like that. So not necessarily looking at integrals or derivatives, but looking at how you can actually prove things, which is kind of interesting. And then you kind of add on top of that, you add on both software engineering classes of how do I create these designs? How do I implement this in C, C++? But at the same time, you also learn computer science theory, again, some of the fundamental underpinnings of computer science, as well as fundamentals of computer systems. Like you get to look at circuits and the design of circuits and how to actually build simple computers. And towards the end, you'll notice that there's a lot of free electives and things like that. And that's actually because as you progress in the curriculum, not only are you allowed to specialize in a specific course, you're also given kind of free reign of what sort of things you even want to be interested in. So that two-pronged approach really helps you a lot be able to hone in exactly on what you want. So again, my interest in software engineering is specifically in geospatial information systems, or software that really, again, works with the world around us. So I was able to pick and choose some courses of interest to me, both from the College of Science and from software engineering, computer science, and IT, and also from College of Imaging Sciences, and being able to pull those things together. So it's really cool. So again, it's very structured early on, but as you progress, you get a lot of free reign in what you can specialize in and what you want. So as far as the classes are concerned, even in computer science, there's a huge focus on teamwork. This is really different than school assignments when you usually worked on things alone, and sometimes in a pair, but oftentimes, except for exams, you're really working on a team of 3 or 4, sometimes 5 people. This means that you succeed or fail as a team. So sometimes it works out awesomely, and sometimes you really, get a dream team, and sometimes, well, they kind of stink. But that's really true wherever you work or study, so it's really good to know how to work with all types of people. And also learning how to have fun in teams is really important as well, and I'm sure you will all hone that skill amazingly. Which kind of brings me to a slight tangent about student life, but hey, it's good stuff to know. My big advice is simple. Just do what you love and the karma will follow you. Get involved in everything and give everything your all, and you can really surprise yourself. For example, these are some highlights from my freshman year. You'll be able to have dinner with Bjarne Stroustrup, the creator of C++. You'll be able to slide around in the mud a little bit during a tug of war in a mud pit. So Mayday, eat your heart out. But actually, no, Mayday is really cool, but they're cool for very different reasons. You also get to hear some really cool people talk. That's Steve Wozniak, who I definitely had to have sign my Apple laptop just because, you gotta do it. And you get to build some awesome stuff. And some stuff ends up sucking, but again, some of it can be really cool. And you meet some really cool friends along the way. And you also still see some of your friends from Harley. So, I was worried that when I graduated that I wasn't going to see a lot of my friends, but you know what? Still stick around. We still stay in touch, and I think that's really cool. And you'll also go to crazy parties. So there's so many more things out there, and you'll pick the rest up from college day. So I'll spare you on that front, but basically know that you're going to win the entire internet. And that's about all the advice that I have. So thank you very much for your time, and good luck. If you have any questions about software engineering, computer science, life as a student, or anything, please don't hesitate to email me at chris@mail.rit.edu or chris@chriscowdery.com. And if you really want to get inside my head a little more, you can check out my website at chriscowdery.com. Cool. Thanks very much for your time.